Okay, right now I'm starting the recording. So let me share my screen. Just move the screen. Sure. I have to play with the screen sharing. Can you see my screen?
Yes, sir. It is visible, but I think your network is.
Okay, let me switch off my video then. Network is poor. I will just switch off my video and then we can discuss here. Now is it good?
Yes, sir. It is visible.
Okay, that's great. So, welcome to the today's session. We are in the week 10 of Fundamentals of Theoretical and Experimental Aerodynamics problem solving session. Professor Arnob Roy is the instructor for this present course, and I'm Gangadhar Venkatramana, this teaching assistant for this course. So, in the last week, we discussed few problems on um, this nozzle flows and supersonic flows. Like it's basically completely a high-speed flow aerodynamics. So this week we will see what are the problems we left in past week and short and few uh, further discussions on this kind of problems. So we solve these kind of questions like as we see. Um, yeah. So as we see here, like we
Sir,
solved. Yes, Arif.
sir, sir.
Uh,
Actually, I am having some doubt regarding the last week. That is week 11. Uh,
okay.
Sir, few
Okay.
assignment
Okay.
questions I have doubt, and I
Hmm.
find the lectures very difficult to understand last week. Like that relay, pitot static tube, and wake analysis. So, sir, can you just
Okay.
give me a brief concept clearing?
Okay. Yeah, I will. We can do that. That is a better thing actually. So I will give you the access for
Okay, sir.
sharing your screen. You have the laptop now.
Yes, sir.
Okay. Just now I gave the access for you to share your screen. If you can share your screen and tell me your doubts, I will discuss with you all. I mean, with you about all those
Sure,
queries.
sure, sir.
Yeah.
Sure, sir.
Yeah.
Just a second, sir. I'm opening the portal.
Okay.
Yes, sir. Sure. Sir, I'm sharing the screen.
Okay. Please share.
Sir, is it visible?
Yes, it's visible.
Sir, sir, actually, I haven't got good marks in this assignment.
Okay.
In multiple answers were wrong because, sir, I was
Hmm.
not able to understand. Sir, in
Hmm.
question 4,
Hmm.
uh, my answer was that thickness at neutral is greater than thickness at favorable and which is greater than thickness at adverse pressure gradient. When we measure it with a pitot static tube, the boundary layer
Hmm.
thickness, basically. That was the concept of the
You
question.
okay? Let me read the question. The boundary layer thickness is obtained by. traversing a boundary layer probe from a station close to the wall and moving it towards the edge of the boundary layer. This experiment is conducted namely three cases: neutral, favorable, and adverse. What do you like? Favorable means that we already stated is negative, right? As professor stated,
Yes, sir.
negative pressure gradient. Yeah. And adverse pressure gradient,
Yes,
what
sir.
he mentioned it exactly.
Sir, in adverse pressure gradient is where the flow is separating.
Where the flow is
Uh,
separating was just separated.
yes. No, sir. In adverse pressure
Neutrally.
gradient, the flow is already separated, and at neutral, the
Hmm.
flow is just in the verge of separation.
Okay. And favorable is negative of dou v by dou y, right?
Favorable is, sir. Yes, sir. Do people. Yes, sir. Means the pressure
So
gradient
these
is
three are.
not negative. It is.
Mhm. Okay. These different cases are studied by using suitable liners on the wall of the wind tunnel test section. Suitable liners that the same streamline stations are used for measurement so that the growth rate of the boundary layer can be compared for three cases. Same stream-wise stations. Okay. If the boundary layer thickness measured for the three cases, delta N neutral, favorable, delta L favorable, that neutral is on the verge of separation, right?
Yes, sir. Yes, sir.
Okay. And favorable plus adverse. Adverse is already separated.
Yes, sir. Adverse is already separated.
If adverse is separated,
Means,
then your boundary layer, yes.
sir, in adverse case, the wake is already in formation. Means wake is already formed in the case of adverse.
Hmm.
So, means according to me, sir, if wake is
Hmm.
forming and the boundary layer is separated from the airfoil or the flat plate,
Hmm.
then the
Hmm.
thickness of the boundary layer should reduce with respect to the neutral and favorable boundary layer thickness. Therefore, I chose the option A, but in answer it came option B and option D.
No, no, no. Can you open a new Google's Chrome and see that how the flow
Yes, sir.
separation on a flat plate or something? Then
Yes,
you
sir.
can get the
Yes,
idea.
sir. Yes, sir.
Yeah.
Pressure.
Flow separation on your flat plate or flow separation on an aerofoil. Flow separation on aerofoil is a good idea. Okay, now you see the schematic or whatever it is. Images. Go to the
Yes, sir.
images.
Sorry. Actually, I am having network issues.
Yeah, same. Out of station actually. So
Okay, sir. Sir, I
yeah, you see
think
this over a
this,
sphere. Yeah. Yes, that is very good. Going to illustrate.
sir, fourth image also it is shown.
Fourth image also you can see, or this
This one,
or
sir.
a sphere also, yes, or a sphere is also you can visualize, or over a airport also you can visualize. If you see the definition clearly, the definition is stating that from the wall surface to a point at which you are having 99% of your free stream velocity is your
Yes, that is the boundary
boundary
layer.
layer.
Yes, sir.
Now you
Yes, sir.
represent where is the delta N, delta A, and delta F. What are the regions of delta A, delta N, and delta F?
Sir, delta F will be in this section before this separation point. Delta F.
Separation point.
Where
So
is,
delta EF is smaller than anything, right?
yes, delta F.
Yeah.
Uh,
Favorable pressure gradient you are telling is a minus dou v by dou y that is inside this below before the separation point.
yes, sir. that will be lesser, and after
Yeah,
that,
delta F is a smaller one. Yeah.
yes sir, after then it is that neutral,
Delta N.
delta n.
Okay. And then
And I am having this doubt, sir, that if the boundary layer is separated, then
mhm,
means in this picture, it is shown that turbulent wake is also inside that boundary layer. But
yes.
in this picture,
Hmm,
if I open this picture, sir, you can see that
hmm.
the boundary layer thickness is decreasing.
That's
Means it
not a
is not
boundary layer thickness. You
that the
have
wake
to
is
clearly follow the definition. Definition of boundary layer is
definition of boundary layer is that the 99 means if we join the points, or if we
hmm,
find the locus of the 99% of the free stream velocity, means the
yes.
velocity of 99% of the free stream velocity, and draw the points joining
Hmm,
it, draw the line
hmm.
joining it, then you will get the boundary layer. But
From
sir,
that is
sorry sir,
yeah. Distance from wall or something else.
distance
That is
from
from
wall sir.
wall or something else.
Yes sir,
Distance from wall.
wall
Yes,
sir.
you should keep in this
Yes
one.
sir.
Yeah. Now you tell
But
me.
I was having that confusion, not with that
Hmm,
neutral and favorable, but with this separation one, that is the adverse pressure gradient. Sir,
hmm,
whenever
hmm,
it is becoming adverse pressure gradient, will we measure the
hmm.
boundary layer thickness from the wall, or will we measure the boundary layer thickness after the formation of the wave? Means, sir, from
No,
this
no,
to
no.
this, or from wall to this?
Definition is always definition, right? We have to follow that. So the definition states you should measure from the wall.
Okay, sir, got it. Actually,
The
I means got the
separation
concept
line is
wrong, sir.
not our wall.
Okay,
Yes.
sir. I got the concept wrong, sir. Actually, there was.
Yeah. Definition you should follow. Based upon that only the question was framed.
Okay, sir. Okay,
Yeah.
sir. The next question is this one, sir. This question I was not able to find the answer. I don't know why,
Okay.
sir, but I followed the formula and concept, but
Mhm.
I was not getting that answer, sir. 1.17. Sorry, 1.07.
Okay, let me read
I
this
just
question.
randomly guessed the answer and just clicked on it.
It's random guess. You did not follow the procedure to solve it.
Yes, sir. Actually, I followed procedure and I was getting 0.9. My answer was
Okay.
coming several times 0.9. I was not able to find the means issue where I was doing the mistake. So that's why I was not able to find the correct answer in this case. I
Okay,
followed the
let me
formula,
see the
sir.
question. Mhm. Drag measurement of circular cross-section cylinder is performed by direct weighing method. Okay. The circular cylinder model is of 12 dia and length of 10 centimeters. It is used for conducting the experiment. It spans the entire width of the small wind tunnel section. Okay. The model is suspended on a drag balance, which uses the weighing method. Okay, before the wind tunnel is started, a weight equal to the dead weight of the cylinder is placed on drag balance weight pan to obtain the initial balance. Okay, so the wind tunnel has started. The test section velocity is adjusted. So the wind tunnel started. The test section velocity is adjusted till the water manometer delta H. Difference in stagnation variable. So for this velocity, the additional weight of 18 grams is put on the pan for balancing. Calculate the drag coefficient on the cylinder. Now, can you tell me how much of grams of drag is acting on this cylinder? Directly from the
It
question, can you tell that?
said drag coefficient or drag
Drag
means.
in terms of grams. Before the wind tunnel started, a weight equal to the dead weight of the cylinder is placed. Okay, additional.
Yes, sir.
Yes,
18
drag,
grams.
not drag coefficient. 18 grams of drag is acting in terms of just
Yes, sir.
grams we are telling, but it is not the correct way. So what is the in newtons? 18 grams means how much newtons it is. Let me also
We have
calculate
to
here.
Sir, we have to convert it in Newton, or
Why not?
from in kg if we kg if we convert it. Oh, sorry, actually I got this wrong, sir. Yes, sir, I got it.
What happened?
Sir, actually it is given weight, so we have to convert it into force. That is multiplied with 9.81.
Yes.
I missed that point, sir. Got it, sir.
Okay.
That's why.
So you can solve it, right?
Yes, sir. Yes, sir. Actually, I followed the formula, sir, correctly, but due to this
Use
slight
the
mistake, I
units
yes, sir.
also you have to, yeah. Units you have to
No, I have
carefully follow.
yes, sir. Actually, I have converted into kg, but I just from my mind, sir. Actually, I have to convert it into force. Therefore, I missed that point.
Hmm. Hmm.
Yes, sir.
Okay.
And these questions, sir, I was not getting, sir. No idea about this question. Question 9.
Like how to solve or
No, sir. How to solve, sir? I didn't get it.
how to solve also you are not so clear. Okay. Let me read
Yes, sir.
this question. A boundary layer probe located near to the flat plate surface is connected to one limb of a manometer. Boundary layer probe located near the flat surface, okay, is connected to one limb of the manometer. The other limb of manometer is connected to the wall static port. What is this? Okay, wall static port, fine. Probe located near to the wall static port. Okay, the proprietary manometric fluid of the relative density 0.95 used in the manometer. The probe is first positioned 3 mm away from the flat plate. 3 mm away from the flat plate, y is equal to 3 mm. A delta H equals to 5 mm is recorded on the manometer. Sorry, recorded the manometer for this position of the probe. Next, the probe is taken beyond the boundary layer thickness. Once you notice no more changes in delta H within region Y. At Y equals to delta H equals to 40 mm. Calculate T U by U infinity at Y equals to 3 mm. Assume the density of air equals to 12.2 kg per meter cube. Okay, so what they're actually doing is they are measuring both the stagnation pressure and static pressure.
Okay, sir.
They did not clearly mention that they used a pitot. Anyway, they mentioned pitot probe.
No, sir.
Can you show
Layer
the
probe.
images?
Boundary layer.
Yeah, they did not. They did not mention it. Like, but they are using both the combination of pitot probe and static probe. Can you show the images once? The flow
Sir,
separation
we
images that we see in just now.
flow separation. Yes, sir. This one.
Yeah, yeah. So let me say like the question is something in this way. What you need to have to find out the velocity from both the stagnation port and the static port. Like you need, sorry, I revealed the answer. If you want to find out the velocity, you need both the stagnation pressure and
Yes, sir.
static pressure. Then can you find the velocity?
Yes, sir. From that we can find.
Okay. From
Sir,
that you can find.
from stagnation pressure and static pressure, we can easily find it.
We can easily
The
find.
velocity.
There,
Yes, sir.
yeah, they have given the same data. What is that means? Suppose assume this is they're saying it's a flat plate. So assume the aerofoil you are seeing in this right side one, and that is also a flat plate. And assume the maximum thickness location. Take the boundary layer profile at the maximum thickness location. Can you point out there? Hover your mouse there at the maximum thickness location.
Maximum thickness location is
A
adverse
boundary
pressure gradient.
maximum thickness of the aerofoil.
Oh, maximum thickness of the airfoil, sir.
Yeah, that point.
Yeah.
That point they have given a velocity profile, right? Can you show the? Can you see? Can you point that velocity profile? The same as where you pointed now. Yeah, that velocity
Yes, sir.
profile. If you consider on a flat plate, okay.
Yes, sir.
If you consider on a flat plate, what they understood is they have a static port on the wall. What is meant by static port on the wall means they will create a port on the wall that can sense the static pressure, only static pressure at that particular location on the wall.
Mm,
It is a port on the wall.
Yes,
Are
sir.
you able to understand?
We are placing the port on the wall.
On the wall. That means we have to drill some hole through the aerofoil
Yes, sir.
and perpendicular to that location, exactly perpendicular to that, normal to the surface. We have to drill a hole and then we have
Yes,
to
sir.
connect a port to it.
Okay. And that port
Then we
will
can
connected to manometer.
manometer.
Okay.
So it is designed in such a way that it can measure the static pressure at that location.
Yes, sir. It will get the, yes, sir. It will find the static pressure
Okay.
at that point. Yes,
Yes.
sir.
So now another thing you have is you have a pitot probe also that is placed above the just 3 mm above the wall surface. They have placed exactly on the same static port location. They have placed another pitot probe.
At that point only, means where we have drilled the
On
hole.
that where we have drilled the hole, but 3 mm above to it.
Okay, sir. Got it.
Just 3 mm above to it, they have placed a pitot probe.
Okay.
And they found that pitot probe what it measures.
So that
Stagnation or
in
static?
stagnation pressure will be measured at that means mouth of that pitot tube, means at the entry point, and static pressure will be on the surface of that pitot tube. So it measures both the pressure, I think. Pitot static tube.
Yeah, pitot static tube does that.
Yes,
But
sir.
here,
Yes, sir.
static instead of static port on the pitot tube, they have removed the static port on the pitot tube and kept inside the aerofoil itself.
Then it will measure stagnation pressure, sir.
So only pitot tube is measuring the stagnation pressure, where your static pressure is coming from the wall.
Yes, sir. Got it.
Okay, that's how they separated. So when they measured the stagnation pressure and static pressure, they found a difference of 14 or some mm of in terms of the manometric fluid they have used. Whatever the manometric fluid they used, based upon
Yes,
that,
sir.
the difference in pressure, it will show the reading in your manometer. Relative
That
density
is
of 0,
5 mm
yes,
del H.
that.
Okay.
For 3, so why it is? Because you have less velocity in the boundary layer,
Okay, sir.
less
And
dynamic pressure in the boundary layer. Now
okay,
stagnation,
sir.
sorry. Then I think you are now a bit clear. Can you explain what they did now next?
Sir, after that, sorry, sir.
Hmm. What they did
Uh,
after this measurement of delta H equals to 5 mm, they did one more measurement. What
yes,
is that?
yes,
From
sir.
the question you can read and tell
After
me.
yes, sir. After that, means after this 3 mm measurement, they had taken that
Hmm.
y equal to 25 mm and saw that the manometer was giving a reading of del H equal to 40 mm. That is the difference between the
Why it
manometric
is
legs.
why it is
Because
more now?
mm, as we are moving towards
Hmm.
oh, actually, sir, at y equal to 25, they have crossed the boundary layer.
Yes.
Is it so? Yes, sir.
Yes.
Uh, and they
Yes.
are
Yes. That is
basically
correct.
measuring the potential. They have went to the potential region, potential flow
Hmm.
region, and measuring it, and therefore it is
Hmm.
giving del H equal to 40 mm.
Yes. That's correct. So now you have a stagnation pressure and static pressure difference in terms of manometric fluid. You can use the manometric relations and you can find the pressure differences and the respective velocity differences, right?
Yes, sir. That we can find.
Yeah. What is the question here is
Calculate.
um, calculate u by u infinity. So you can calculate the velocity in the boundary layer and velocity outside the boundary layer.
Yes, sir.
Velocity outside the boundary layer is itself u infinity.
Got it, sir. Got it.
Yeah,
Got the concept.
that you can try. Yes.
Okay, sir. Thank you, sir. No more questions.
That's all. No more questions.
Sir, yes, sir. Another question. This question I have got it right. This question number
Hmm.
6. But basically, sir, I was not able to understand that in the lecture video about this wake analysis, wake survey. If you can separately make me understand this concept of wake survey using the Rayleigh Petot arrangement.
It's an integration of wake momentum deficit concept that you are trying to understand.
Yes, sir, momentum deficit concept. That control volume, actually they were taking the professor was taking a control volume around the airfoil and the means wind tunnel, and after that he was analyzing that control volume, means the different that wake formation at the trailing edge, that momentum deficit. So that only I could not understand that concept.
Okay. I don't see any difference between equation 1 and 2. They both looks like same to me.
Yes, sir. Answer I have got
Equation
it
A
correct.
and B. Yeah.
From mathematical perspective, sir, I understood that mathematical perspective what professor was trying to tell, but sir, that analysis portion I was not able to understand.
For what they integrated it from like change in, I mean, decrease in momentum. Rho is mass into velocity. Yeah, this is for mv squared. That's it. Like, what is the momentum equation or the kinetic energy? You can say, Arhit.
That's half mv square. Okay.
Half mv square. Okay, that is for your kinetic energy. The same thing they are trying to use here.
Okay, sir.
I don't see anything difference that you can see here. It is same as
No, yes, sir.
your
Both the equations are same only.
difference in the kinetic energy that they are trying to show here, but actually it is something still like related to your concept of boundary layer while you're trying to measure the momentum thickness.
Okay, sir.
Somehow looks like the same, that we can figure it out. I will show you, like, if you can show me the video at lecture what actually professor is
Yes, sir.
showing
Sure.
this, then I can describe you.
Measuring measurement of pressure using Rayleigh Petot to track Yes, sir. This portion.
Yes, you can find. Yes. Now, can you forward a bit?
Sorry, sir.
This is the momentum deficiency concept. Like, based upon your momentum deficiency, you can calculate the drag experiencing by the fluid. This is very important concept. You can forward a bit.
Yes, sir.
That is for the surface forces. Next.
Surface force after that.
Any surface. CD and FG balance and each other. What is this CD and FG?
CD and FG is that sir part of that airfoil. Actually, professor has named it CD
Okay,
and
C
FG.
and
This
D and
portion.
FG. Okay,
Yes, sir.
okay, yeah.
The wake region.
Okay. total surface force on the entire CD. Momentum equation. So do you remember this momentum equation?
No, sir. Actually, I forgot about this. In week 3 or week 4, I have studied about
it. It is a part of a Navier-Stokes equation there where we started.
Yes, sir. Yes, sir.
Yeah.
It was part.
Yeah.
Part
Yeah.
of that.
So using that momentum equation only, they're trying to
The
make
x component of momentum equation, from that said
X
drag per
component of
unit span professor has calculated, and they have said after finding that drag per unit span, it was an assumption that P is approximately becoming P infinity. That is pressure of the
it
free
becomes P infinity. Yes, it becomes P infinity also. Even if you measure in the wake, the P becomes
sir.
there at the particular location. Maybe at some point you will get low fluctuations, but it actually P becomes P infinity.
Okay, sir.
Mostly the
So
difference will come on the airfoil only. Okay.
okay, sir. Then after that, sir, professor has found that V dot ds is equal to 0. That for
So
streamlines.
that's for streamline. But did you get the reason why how he calculated the drag by
No,
using this momentum equation formula?
no, sir.
From his momentum equation, he acquired that surface integral of rho v bar ds bar times u.
No, sir. Yes, sir. From this equation, when P dot ds equal to 0, after that, sir, this equation is coming d equal to surface integral P dot ds
No,
into
no.
u.
Yes. Yeah, that is the equation that you have to understand how it is coming. It is from the momentum equation that you have derived in the past lectures.
Yes, sir.
So you have to get like you can refer that concept once again, then you can understand up to here. And just the same thing that you used for your previous analysis also. So what is the next equation that he derived?
So after that, surface integral P dot ds, he has expanded it, and from that, using the applying continuity equation in the control volume, he has acquired this equation. This one minus rho u2 u1 minus u2 into dy. This was the final equation. After that, sir, putting the value of pv dot ds into u in the drag, we are finally getting this non-dimensional dimensionless CD. Means the drag and putting it into that equation of CD will be.
Can you move backward a bit?
Yes, sir. Yes, sir. Yes, sir. Sir, last slide.
The previous slide to this.
Yes, sir.
Why he put 2 into u1? Any reason for the 2 into u1 or 2 into u2? What is that? Yes, 2 into u1. Total u2 equals to 0. That is the momentum conservation. So how he applying it as 0 for it? Like we are mentioning it as this difference as a drag coefficient, right?
Yes, sir.
So how this 0 comes?
So that applying continuity
This
equation.
is continuity. This is another equation, right?
Yes, sir.
Not this integral. Okay, this is the continuity equation. That is the momentum one. This is bit okay. U1
Sir,
square,
just
U2
a
square.
second, sir. Just a second.
Yeah.
Yes, sir.
Okay. So I don't see any difficulties in understanding this mathematical logic, but theoretically where you are missing, like any problem that you're facing that I don't understand this part or something like this.
Sir, actually, means I was facing, means I was not able to recall that momentum equation derivation, the basic fundamental concept.
Which equation?
Uh, Sorry, sir.
Which equation? I didn't get you.
Sir, that momentum equation from Navier-Stokes equations, how it is derived. I think I need to revise it once again, sir. Then I will-
Yeah, momentum equation from the Navier-Stokes, you have to revise it. Unless you revise that, you
Yes.
cannot uh, frame this kind of. But it is again still simple that if you go back to the momentum equation, you always can recall like that. Can you go back to the momentum equation?
Yes, sir. Yes.
No need to. Here only in this video itself, you can find that.
Oh, sir, last slide.
Yeah, previous slide he wrote the momentum equation right there. You can find it.
Sir, yeah, this is the
One more
drag
slide.
equal to.
Before. Take X momentum equation. Suppose one more slide before. Or else you can use this one also. That's not an issue.
Yes, sir, this one. That volume integral del by del T volume integral PV dV. The surface integral PV dot ds vector V equal to H.
Yes. Yes. So this is the equation that we need to focus on. Actually, here the momentum equation is something like first is the acceleration term.
Sorry, sir.
First is the acceleration terms. All your
Yes, sir.
terms represent your acceleration, and then rho v bar ds is rho v bar ds dot v bar is your volume integral and surface integral and your forces. First represents for acceleration terms and surface forces. The second term represents your surface forces. And the third term represents the additional forces that you are acting on the system. If I'm not wrong, which is what he wrote here. Yes, first is the acceleration terms, and the second one represents the surface forces and the resultant forces. So this is a summation of your forces, all the forces. Or you can use the second
Yes,
law
sir.
of Newton's also. The same
Yes, sir.
thing. Okay.
Okay,
You
sir.
think from the simple mechanics, like what is this term represents? All these terms are representing some forces acting on the body, or forces of acceleration. Acceleration forces is the first one.
Okay, sir.
Okay.
Okay, sir.
Okay. Any more questions?
No, sir.
Okay, Arhat, if no more questions, I will stop this recording. I'm not stop this recording. We can meet again at what is the time now? 6:40, right?
Yes, sir.
6:55. Okay. Yeah, just a 15
Okay,
minute
sir.
break. It's a small long break because I have some issue. We can meet that again 6:55.
Okay, sir.
Sorry. I will keep this meeting like this and then we can meet at 6:55.
Okay, sir.
Okay. Thank you. Welcome back. Parhit, are you there?
Yes, sir.
Yeah. Welcome to the session again. So, Arhit, I just want to like, do you have access to your pen and paper there at your side?
Yes, sir.
Okay, can you just see the last query from some student in the discussion chat? The same question, like whether about that you said we discussed in the just before the break. Uh, week 10 assignment and question 9. He's trying to find the solution, but his solution is not in the list of the correct answers. So we can just give a trial to answer that question.
Okay, sir.
Just can you show that if you have pen and paper
Yes,
access
sir.
there, is
Yes.
it possible for you
Yes.
to do that?
Yes, sir. Yes, sir. Yeah.
That's good. Yeah. Yes. Just show the question once. We can try to solve it here so that we can pin it later to that particular person or everyone. Can you share the screen and show me the question also?
Yes, sir. Yes, sir.
If everything is okay from your side. Yeah.
Yes, just a second.
Yes. Yes. Yeah.
Sir, is my screen visible?
Yes. It's visible.
Mm, sir, where I have to go?
Assignment 10, question 9.
Okay, so question. Yes, sir.
So we are at assignment 10 and question 9. Yes, this is the one. So he is arguing something like his answer that he is getting is something, and like he also cross calculated several times it would. So we can just re-verify this numerics and whether what, and let's see what we are getting from our calculations. Okay.
Okay, sir.
Okay. Let me take a screenshot of that. Where is this? If you have a pen and paper access, you can start it, right?
Sir, working on it, please answer.
Yeah, we will try to solve this question. I will also share my screen, but before that, I just want to take the screenshot. It is not working. Give me a second. I'm just downloading this. So have you started solving this?
Yes, sir, I'm trying to solve.
Yeah. Please do that. We will see this.
Sir,
Yes.
hello.
Yes,
Sir,
sir. Yes. Tell me.
actually, sir, you told that this
Hmm.
static port and the probe is at the same position, same point. Sir, is it so? Because
Uh,
it is connected to two legs of the manometer. So how
hmm.
can it be at the same position? Like, can't
I
understand. Sir,
didn't
if
get
you
your
can,
question.
sir, can you
It is
just
something.
draw the arrangement?
Can you see the screen?
Yes, yes, sir.
So suppose if this is your wall and somewhere like this, your boundary layer is like this. They are tapping the pressure something like this. This is your static pressure port. So they
Okay.
connected this to one of your YouTube manometer. It is not the correct representation of YouTube manometer. So this is your static port. Okay. And uh, just assume the lines as your static and
Yes, sir. I got it.
you got it?
Yes, sir. Actually, I did the same. The arrangement, but I
Yes.
was thinking only that is that.
Hmm. Now you have difference is like as you connected to the true legs of manometer, your stagnation pressure, I mean the limb in the right side, whatever the stagnation port you connected, that has more amount of pressure on the top, so that's why it is lower.
Yes, sir. That is,
And
we
this,
can. So if we name the 2 points, that the
hmm,
static point as one and oh,
yes,
sir,
we
another
can.
thing, sir. This probe, the end of
Hmm,
that probe is
hmm,
vertically means at the same line of the static port.
yes,
Oh, got it, sir.
exactly on the same line.
Okay,
At
sir.
the first, it is about 3 mm height.
Okay, sir. So, sir, P2 minus P1, sorry, the stagnation pressure minus static pressure equal to del H rho G, we can use, sir, from that.
Rho G delta H you can use.
Del H rho G, from that, sir,
Hmm.
using the velocity equation that V equal to root over 2 into P2 minus, that is stagnation minus static divided by
Okay.
rho. From that
Hmm.
equation, we can find the
Half
velocity
rho
also.
v square.
Yes, sir.
P
From
naught
that
minus P equals to half rho v infinity
rho V
square,
square.
right?
Yes, sir. From that V infinity, we can easily find out because we have find out P naught minus P from del rho
Hmm.
GH.
Del rho
Del,
gh,
sorry,
because P naught
del
minus P
H
is
rho
again
G.
equals to
Uh,
difference in the pressure of the limbs is rho g del h. Okay.
rho
So
G
you
del
can
H.
find the P naught minus P, or you can use this because here P naught minus P is this is the manometric liquid. I will just write it clearly. This is rho manometric liquid, and this is
Into
gravity,
1000.
and this is delta H. Yeah,
Okay.
950 kg per meter cube into, you can use 9.81.
9.81 into 0.05.
Delta H is
0.005.
how much for first one? 5 mm. 0.005. What is this P naught minus P infinity difference?
That is 46.59. It is coming, sir.
40?
46.59.
46.59, or you can, okay, you can do like this and find the answer, and I will also directly use and simplify. Rho g delta h equals to half rho v infinity square or something, whatever the v is there. I will just use this v. So what you will get, rho m by rho of air. I will say it is rho air, and g delta h equals to, so 2v square, 2 times, what is this, 950 over 1.225. Is that 8 they gave or something
Yes, sir.
else?
8.81 answer is
Zero.
coming.
How much?
V equal to 8.8119.
Equal to 0.9, right?
Yes, sir.
119 or 819?
Double 19, sir. Means there are multiple
Okay.
digits after that also, but I just took full digit.
So it is now our V1. V2 is somewhere at the height. Use the
That is,
same
sir, V.
procedure.
Sir, this is depicted as U, and another velocity that we are going to find, that is the if we place the
V2.
V2. Sir,
Yes,
V2
some
means the
height.
potential flow at 25 mm.
Yeah.
Potential region. Okay, sir.
Height is 25 mm. Yeah, height is 25 mm. Sorry, like location is 25 mm, but delta H is 40 mm something, right?
Yes, sir. Delta H is 40 mm. Yes,
Hmm.
yes, sir.
Yeah.
40 mm.
Yeah. You can use that. What is this V2 here? Eight point 819 meters per second is too high. Okay, let's see. 40 mm, 0.95. Harith, did you calculate the answer for this? V2.
Sir, actually, I'm getting it wrong, sir. Just a second, sir. I'm rechecking my calculation once.
Okay, fine. Yes, I'm getting 24.670.
Sir, V2 is correct, sir. V2 and V1 both are correct. That is 24.62. What you have got, that is only right. But it is not matching with the
Okay.
answer, sir.
So if it is not
Oh, 1 second, sir. Just
matching, we will also post same thing. Anything that we
8.8
missed to.
divided by 24.9258. 0.35 it is coming. Yes, sir. Second option. Correct, sir. Got it. With the last calculation.
0.35. This is the ratio. What
Yes,
is the
sir.
answer
Yes,
they
sir.
have given?
0.35 only, sir.
Option B is that is 0.35 is not matching with the calculation. So answer is 0.35 only, right?
Yes, sir. 0.35 only.
Yeah. Okay. If you have some time, or else later I will post this video, and then that particular person can refer this. Someone questioned this, we can refer it later on.
Okay, sir. Sir, actually, this question was
Yeah.
easy, but I was not able to grasp that arrangement. How you told here, like that the static port and the pitot arrangement. Actually, I thought that pitot and static tube. So, because pitot static tube both measures the stagnation pressure and static pressure. So I was a bit confused about the arrangement and the probe. So you just cleared my conception there. So I was not able to solve this question, sir. So due to that reason.
Pitot, yes, pitot represents the stagnation and static represents, static represents the static force. That's it.
Yes, because
You can
actually,
find
sir,
this by
in
just by
yes, sir. In professor's video, sir, actually what professor has shown in the videos, the arrangement of pitot, that pitot tube, he has shown the pitot and static tube. It has both the arrangement for measuring stagnation pressure and static pressure. So I was not able to understand whether, sir, how can we, sir, find like we are also drilling holes for static pressure measurement, and also the pitot tube has both the arrangement pitot and like stagnation pressure and static pressure. So I was a bit confused with that.
Yeah. Understand. So let's now let's solve a few more questions, and then we can wind up this session today. So do you have the questions? I think you don't have the questions of it. Let me write the data instead of question. So the question is like this. Are you able to see the screen, right?
No,
My
sir.
screen, my mobile screen.
No, sir. FETA it is that blackboard only showing.
FPTA, yeah, that one only.
Yes, sir. Yes, sir.
Yeah. So next question is something like this. I'll just write here because I don't have the option. This question is, what is the correct for the following statements? They are asking two statements. The statement one is like this. Supersonic flow turns into itself. It forms on shockwave. Similar supersonic flow turns away from itself, forms expansion waves. Which statement is correct? Do you have any guess?
Sir, just a second. I'm reading it. Supersonic flow turns away from itself, it forms expansion wave. Supersonic flow. Yes,
Expansion, fan
statement
or
2 is
expansion.
statement 2 is correct, sir. And turn
Why
normal
not
shock
statement
waves.
one?
Just a second. It says supersonic flow turns into itself. It forms like if we have a compression corner, sir. In that case, normal shock. Yes, sir. Statement 1 is also correct. Both the statements are
Statement
correct,
one
I
is
think
also
so.
true.
Supersonic flow turns into itself. It forms normal
Hmm.
shock wave. Turns it into itself minus means, sir, that it is going through a compression corner. Is it so?
Compression corner, yes.
Then, sir, it will form a normal shock wave or oblique shock wave. Sorry, oblique shock wave it will
Yes,
form.
it forms the oblique shock wave.
Statement 1.
So
Yes,
first
sir,
statement
statement 1
is
is wrong. It is false, sir.
yes. The statement one is false. Okay, so that is the question. We have few
Yes.
more good questions. Let's try to attempt those. So in this question, you have a right. You have a blunt nose body, and you have a bow shock here. Have you solved this question before? What I am trying to
Sir, I have to
solve.
recall it.
Fine, fine. Not an issue. So this is your blunt body. So if you are having a supersonic flow, that pre-stream max number is greater than 1. And because of this blunt body, it formed a bow shock. This is a bow shock. So the question is now, which region you can estimate the flow or the phenomena acts like a normal shock wave? Region 1, region 2, region 3. Which region you can estimate or you can approximate that bow shock acts like a normal shock wave at that particular location?
Sir, is it location 2?
Yes, it's
It will be location 2,
location
sir.
2, right?
Hmm.
Yes, this small region, not for the very long region, for very
Yes, sir. For very small
small
region,
region can be approximated as normal shock wave. Okay.
yes, sir.
Yeah. So next question we have. This is an interesting question. So you can easily answer this. So let me write the question again. We have 4 governing equations. These equations always you should have in your mind if you want to, like, if you're a high-speed aerodynamist, always these equations should come into your picture along with the assumptions behind these equations. It's a bit different, but you can still use for this low-speed aerodynamics also, except the energy equation. You can also use the energy equation, but there won't be any temperature difference, and you'll get everything nullified. So which of these equations can be used or cannot be used for a normal shock wave properties? Let me first ask you each equation. What is its importance? What is this first equation?
Sir, first
Importance.
equation is that importance is it determines the rotationality of the flow.
Rotation
After that,
and irrotationality of the flow. Okay, I will
no.
just write whatever you say. You can use Google, not an issue, open book kind of thing. You can use Google and see what is this del dot v bar equals to 0.
So actually, curl of vector v is equal to, if it is equal to 0, then it will form irrotational flow. This is divergence of vector v velocity field is equal to 0. That
Divergence
means
of
it is rotational
hmm.
flow. I think so. Just sir, I need to check the Google. Sir.
Check it. Not an issue. It is
Divergence
open book and for you. Divergence of velocity field.
velocity
Divergence.
velocity vector. The
Divergence
divergence
of velocity field. What it represents.
source lines in flow. The divergence of the is the rate of expansion of the fluid per unit volume.
There your answer lies.
So is it that source flow?
No. The divergence of velocity field is correct, but what it signifies?
So I need to check my notes, sir.
That is
Give
fine.
me a second, sir.
Actually, you are really putting good efforts. Yeah. If you
Actually,
don't take
sir,
time, then it's fine.
due to my semester exams also, I'm not able to recall the past lectures. So just give me a second, sir.
You're really doing very good. Yeah. Yeah, fine. Take time. If you did not find anything, I will tell you. I will help you.
No, sir. Actually, I noted that Laplace equation, that governing equation for irrotational flow, but the divergence
That's
equations
fine.
are
That's fine. It's
finding, sir.
that's fine.
Sir, curl of velocity vector v, if it is 0, then it is vorticity
I will
will
just
not
help you. Like
be.
you can
No,
refer
sir.
it
I am
later.
not getting it. I'm not getting it. Sorry, sir.
It is actually the representation of incompressibility.
Oh, yes. Yes, sir.
Where your incompressibility does not relate with your density. Incompressibility is something like your volume is not changing. Okay.
Okay,
So
sir.
this is a representation of your incompressible flow. When del dot v bar equals to 0, there is no compressibility of any fluid element. It is not changing its volume. Okay. So that is
Okay,
what the
sir.
representation.
So
People used to say
representation
this
of
is also a steady content. Yeah.
representation of
Representation.
incompressible flow.
Yes, representation of incompressible flow.
Okay, sir. But if we say, sir, del rho by del t, if it is 0, then it can also be shown as a representation of incompressible flow.
Yes, that is the constant density flow. Del rho by del T naught, d rho by dt, capital
Yeah,
D rho
d
by
rho by
capital T.
Okay, sir.
This is your constant density flow and your d rho by dt equals to 0. But del dot v bar equals to 0, then that is your incompressibility. You can get much more clarity. Just revise this basics. Once you revise, you can get much more clarity why I'm stating like this.
Okay, sir.
People
Actually,
used to
sir, I
call it
got
as
this.
a continuity equation also.
Okay, sir.
Yes, it is a
Actually, I
continuity equation. Yeah. Tell me,
got
tell
this
me.
answer. I got this answer wrong in interview, sir. Then I said that d rho by dt is equal to 0. If it is 0, then it is compressible.
That is
Incompressible.
also fine. That is also fine. But when you come to the higher standards, then they will expect accurate answer. But when you say d rho by dt is also equal to, that is also correct. When according to the situation also, that is also correct. So, certain conditions, that's it. Not a big issue. Okay.
Okay, sir.
Yeah. Then the second one. What is the second one you have?
Rho 1 u1 equal to rho 2 u2. Is it
Yes.
continuity? No. a1 b1 rho 1 equal to sir, is it means that if the area is a1 is equal to a2, means
Yes.
if I can say that it is continuity equation, because a1 b1 rho 1 equal to a2 b2 rho 2.
Equation in 1D form, one dimensional form.
Yes, sir, 1D form.
This way.
P1 plus 1 by 2 rho. Where is 1 by 2? It's not coming. It is Bernoulli's equation. P1 plus half rho v square equal to P2 plus half. No,
There is
this is
no
not
half.
Bernoulli. This is not Bernoulli equation. So is I think. Just a second. Momentum.
This is the momentum 1D
Yes, sir.
form.
Momentum equation. Momentum 1D form.
This
And
way.
the last one is energy equation. This is energy equation.
Energy 1D form. Okay.
Yes,
So
sir.
which equation is not applicable for the shock waves? That is the question. Which equation is not applicable to the shock waves?
Continuity equation. I think
Why
it is not
continuity?
applicable. Sir, because no, sir, if we analyze the supersonic flow before and after a normal shock wave, then there will be a means decrease of pressure in a sharp slope. Means the pressure decreases very sharply. So in that case, sir, energy equation is correct. Divergence of velocity incompressible. It is also correct. So I think it is continuity equation.
You should be clear that continuity equation is applicable everywhere. Unless there is a mass disappearance or mass generation, continuity is applicable as everywhere. Continuity, momentum,
Okay.
energy, they are applicable everywhere. The only
Then
thing
sir,
is that is not conserve incompressibility. Yes, incompressibility has no conservation. Okay.
Okay.
All remaining properties are conserved. Like you cannot destroy them or you cannot generate them. They are applicable for everywhere, normal shock wave or whatever the form it is. Okay. But
Okay, sir.
incompressibility, like there is no conservativeness for this, so you can apply for only for specific times. So the
So, sir,
answer
in case,
is,
sir,
in
momentum
case,
is also conserved, energy is conserved, and mass is also conserved. So, in these both
yes.
2, 3, and 4, the three conservation principles, we can from that we can say that it will be correct to assume that it will be conserved in any case, in normal, oblique, or bow shock. Only the changes incompressibility. That is, incompressibility will not fit in this case.
Incompressibility not fit in this case. Yes, and because those are all compressible flows.
Okay, sir.
Normal
Like
shock
these are
wave we are dealing with, the flow should be compressible.
okay, sir.
Right.
Yes, sir.
Okay. We have one good question now. I will just ask you the things. You can tell me the question. For a supersonic flow and normal shock wave. For a normal shock wave is just like this. Assume is a very thin layer of a shock wave. This is region 1 and this is region 2. And you have some options. State which option is correct. U1 and U2. Greater than or less than?
Sir, U2 will be less than U1.
Right? Let it,
Yes, sir.
let it come up.
U2 is less than U1.
Okay. And second one is M1, M2. What should I write? Less than or greater than symbol?
The momentum. Sorry.
Mach number. M.
Oh, Mach number. Sorry,
Mach
sir.
number.
Mach number will decrease, sir. M2 is less than M1.
Fine. Then static pressure. P1, P2.
U1, P2, static pressure. If U1 is, sir, just a second, sir. Pressure will decrease. So velocity will increase, sir. That is, U2 must be greater than U1. That is, P2, if P2 is less than P1,
No,
P2 is
I'm
less
not
than.
telling anything. Which one is correct? P2 is greater or P1 is greater? Just asking
P1.
you. I can change the symbol. I can change the symbol greater than or less than.
Okay, sir.
According to the shock wave, I'm asking. Your flow
P1,
is
sir.
like this. P1 is
Greater, sir. Static pressure.
P1 is greater.
No, sir. P2 is greater.
P2 is greater. That is right. Let's go to the next question. And then P01, P02. Which one is?
Stagnation
Can
pressure.
you see this?
Yes, sir.
Just tell me whether it is greater than or not. Fourth one. You just recall, take your time, recall, and tell me. Because this is the session for you.
Okay, sir. Sir, can I Google it?
Yes, it's an open book. You can try anywhere. You can see it anywhere. It's not necessary to remind everything. You can Google it and you can redirect with things and you can tell also. Or else if you are unable to say answer, but take less time, don't take much time. If you are unable to say answer, just tell me and I will reveal it.
Okay, sir. Sir.
Hmm.
So T1 is equal to T2.
T1
And
equals to T2.
yes, it is sir adiabatic, and P01, that stagnation pressure, always decreases across a shock wave.
Decrease means I should use the less than symbol or greater than symbol.
In so P0
Like this.
P02 is less than P01.
P02 is
The
less than P01.
stagnation the stagnation pressure always decreases across a shock wave
Hmm.
due
It's
to
like,
increase in entropy.
okay, now, okay, that is correct. Stagnation pressure, what you said is correct. And what about temperature, static temperature?
Static temperatures are actually in mm, normal in case of shock waves, sir, it is an basically adiabatic in nature. So, sir, if it
Hmm.
is adiabatic, then there is no heat flow, so the temperature will be, sir, same only, I think.
That is the case. What is the stagnation
Oh,
temperature
again, sir,
change?
stagnation and static.
Hmm.
Yes, sir. Sir, can I answer the sixth one, because I'm not getting this two.
Okay. Yes, yes. Why? Any question you can answer.
Sixth one will see, and entropy will increase, sir, across the shock. So S2 is greater than S1.
Okay.
Uh, T1 and T2. T1 and T2 case. No, sir, I can't solve more. Yes, I recall
Row
this.
1, row 2.
Density. The density increases across the shock wave. Static pressure also increases across the shock wave.
Static pressure
Static
is also
temperature.
done.
Sorry,
Density.
sorry. Static temperature, sir. Static pressure, static temperature, and gas density increases instantaneously across a shock wave.
Okay. Then what about the
So,
stagnation temperature?
yes, a stagnation temperature. Check. Does not change, sir, across a shock wave. Stagnation temperature.
Now tell me the facts. Are you able to see the screen? Like, is it updating
Yes, sir.
on the screen?
Yes, sir. Yes, sir. I'm able to see.
Yeah. Now tell me the facts. What do you
Sir,
understand?
trap
Why it is
is
happening like this? Stagnation temperature. Think from the basic ideas that you remember from the shock wave. Then we can discuss it. Like, you have any question or doubt in this? Why these properties are like? Because you already googled it, and you might have
yes, sir.
said the same answer what Google told. But do you know
Yes, sir.
the
Yes, sir.
correct answer and reasons behind it? If yes, tell me all about all these 1 to 8 properties. Tell me how it is happening.
Sir, except one and two, I have googled all the. Frankly speaking, I have googled all the answers except one and two,
No
because
issue,
as
no
per,
issue. Even you googled it, you can tell the answer in the by checking in the Google also. That is
yes,
also
sir, because sir, one and two, I can recall, because Mach number decreases across a shock wave. These I can
okay.
recall, and this velocity also decreases
Hmm.
across a shock wave,
Hmm.
and this
Hmm.
pressure, and this was the reason, sir. There was a graph plotted by professor, and he showed that
Hmm.
how it
Hmm.
decreases sharply or instantaneously. We can say that how velocity
Hmm.
decreases instantaneously across a normal shock, and the
Hmm.
Mach number also decreases across a normal shock. The reason
Hmm.
I am not able to recall, or sir, I haven't searched it further. Why is it like that?
Okay. The thing is, for a calorically perfect gas, We are only talking about a calorically perfect gas.
Okay.
That means your specific heat ratio, like not specific heat, Cp, Cv, or keeping those things as constant. Calorically perfect means that you are keeping your specific heat at constant pressure, specific heat at constant volume. You are keeping those things as a constant. So those kind of perfect gas, we are talking only about that kind of perfect gas. And if that gas is facing a normal shock, somewhere in the flow of that gas, you are keeping a normal shock or you are generating a normal shock by some means using a shock tube or something. Okay.
Okay, sir.
So across the shock wave, it is approximated that for generating these kind of relations, it is approximated that the flow is adiabatic, but it is not isentropic. What do you understand?
Sir, it means that if it is adiabatic, like the temperatures, the stagnation temperature will be same, and isentropic, if means the entropy will not change. Sorry, it is not isentropic. So the entropy will
It
change,
is
sir,
not
across the shock wave.
sorry, sorry for that. Yeah, the entropy will change across the shock wave. If it is adiabatic, the temperature
Stagnation temperature
remains.
will remain same, but static temperature will change.
Yes. The static temperature will change. The stagnation temperature remains same. The adiabatic means that is
Yes.
the thing. When you have the
There is
stagnation temperature change, there should
yes,
be
sir.
some energy exchange.
Yes, sir. Yes, sir.
I'm not saying
That means
energy
that
decrease or
heat,
increase.
yes, sir. Heat energy must be means there must be if it is adiabatic, there is no heat energy exchange between before and
Heat
after the
energy
shock.
exchange. Yes.
So, sir,
We should not
that
say heat energy decrement or increment because increment or decrement is not the correct terminology. Exchange is the correct terminology.
yes, sir.
Something should be there to take this energy, right?
Yes, sir.
Yeah. So energy is constant. If energy is constant, your stagnation temperature is
Sir, if energy is constant, stagnation temperature will be equal.
is equal. So T01 equals to T02. That is fine.
Yes, sir. Yes, sir.
Okay. Yeah. What next? Density. What
Density.
about the density? Yeah. Density will decrease or increase. What is like you tell from the basic perspective, your velocity increases or decreases after the shock?
Sir, velocity decreases.
After the shock, velocity decreases. So think in a general perspective, if velocity decreases, like significantly or just a small amount it decreases?
No,
Very
it's
huge value it
decreases
decreases, right?
significantly, sir. Not small value.
Significantly, a high amount it will decrease. So if there is a high velocity decrease between region 1 and region 2, uh, what about the pressure? There is a thing like high pressure, sorry, high velocity and low velocity, how the pressure differs. At high velocity, you have low pressure, and low velocity, you have,
High pressure.
yes, the same, vice versa. You have two different regions from high pressure and low pressure, from where to
Sir,
where your velocity flows.
uh, sir, I have a question regarding this.
Hmm.
Sir, you just told this that if velocity decreases, the pressure will
Hmm.
increase
Yes.
and the density will decrease. Sir, can we just
Density,
say
I
that
did not
from
say that density decay.
okay? Can we, sir, say
I
this
did not
from
say that.
that Bernoulli's equation because Bernoulli's equation
You can still.
for
Uh,
for incompressible flow it is applicable, but for compressible flow, Bernoulli's equation is not applicable. So
no,
if
I'm not
density is
saying from
changing,
the complete Bernoulli's perspective. I'm saying from this equation perspective. The equation is just made right.
okay, sir. Momentum equation. Yes, sir. Momentum equation we
is
can.
very close to U2. So you see from this equation, if U1 is greater than U2, we have two more variables to decide the pressure and density, right?
Yes, sir.
You know that U1 is far greater than U2. So if
One is yes, sir.
and you also know that actually if you see the properties, not because of the velocity, it actually compresses all the fluid. So your P2 is way greater than P1, stagnation pressure, where it's a static pressure, where your stagnation pressure, there is a loss of stagnation pressure. P02 is less than P01. Static pressure increases significantly, static pressure, but the stagnation pressure decreases. You have to be very
Okay,
careful
sir.
with it. Okay.
Okay, sir.
And your density rho1 is way less than rho2. Okay.
Okay, sir.
Density is very less, rho1 is very less than rho2 because assume it is like you are compressing by a piston. Then you can clearly understand. Some flow is there and then you are compressing it with by a piston.
Yes, sir.
What will happen? Your static pressure increases and your density also increases, right?
Yes, sir.
Density increases, static pressure increases because stagnation pressure loss. This is actually the
Yes, sir.
stagnation pressure is some kind of energy loss. So that is because of your shock wave, normal shock wave, and your entropy increases. Entropy always increases, right? And
Yes, sir.
then your stagnation temperature keeps constant because we assumed it as adiabatic, right?
Yes, sir.
Yeah, so these are the essential things that you should always keep in your mind. What are the properties, how it acts for a normal shock wave? Okay,
Okay, sir.
if that is the case, I just shock waves. We have few more questions here actually. Let me see if there are any small questions we can solve it today. Do you have the formulas of a shock wave?
Sorry, sir.
Do you have formulas of a shock wave with you?
Sir, I need to check my notes.
Okay, that's not an issue. So the question is like this. A normal shock wave is there, very thin normal shock wave. A very thin normal shock wave is there that has Mach number m1 equals to 1.5 and m2 equals to question. This is the question. And they given that gamma equals to 1.4. Can you find what is the m2 from the shock wave relations?
Yes, sir. I can find it. The formula is there,
Yeah, what is that for?
but I need some time to solve it because
You
I
can,
have
you
to
can
see the formula.
just recall where it is and see the formulas and let me know.
Okay, sir.
This is generally in the form of m2 square. Just a minute, Arhit.
Yes, sir.
Arhit, did you find the equation?
No, sir. Mm, Just finding it,
Okay,
sir.
let me show you the equation. Fine, fine, that is not an issue. I will just write the equation. You can just later on recollect it. So if you want to find the Mach number behind the chalk, this is the relation that what I'm writing on the screen. No need to remember these equations. Equations are big, you will get in the exams, but some important equation you should always keep in your mind, like the continuity equation, those kind of things. So once you have
Okay,
this
sir.
this equation, you can solve it that by substituting what is this? Gamma equals to 1.4. Yes, gamma equals to 1.4 and m1 equals to 1.5. If you substitute that, 1 plus 0.4 over 2, 1.5 square over 1.4 times 1.5 square, 0.4 by
0.4 by 2.
2.
Sir, it
All
is
that you
easier.
will get m2 equals to 0.7. So it is easier for you. You can solve it easily. So see that m1 is greater than 1 and m2 is less than 1. So this is
Yes, sir.
what the normal shock wave. You have, so you should have supersonic flow at the upstream and it will make it as a down, like subsonic flow. Okay.
Yes, sir. Sir, this
Yes.
concept is used in the CD nozzle, I think so, because they are forming that normal
Yes.
shock wave at the throat and thus decreasing or increasing the Mach number.
Yes. Not the throat in the divergent section.
Normal shock
The
wave.
divergent section you will see the normal shock wave. At throat you
Yes,
will
sir.
get a choke. Mach number equals
Yes,
to
sir.
1.
Sure. Yes, sir. Yes, sir.
Yeah, that is the another different concept. So if you have any queries, we can discuss those things in just for a few minutes. If not, we can end this session.
No,
You
sir.
have
I
any
don't.
queries?
No, sir.
You don't have any. Okay. Okay, then thank you, Harit. Thank you for joining today.
Thank you,
I
sir.
will see you in the next session.
Okay, sir.
Yeah, bye. Keep
Bye, sir.
recalling the past lectures. Just if you have some time,
Yes, sir.
other than your
Sir.
exams, focus on your exams first and
Yes, sir.
then recall the lectures. It's not a primary. First, your exams is a
Yes, sir.
primary. Okay.
Sir,
Yeah. Yeah.
actually,
Bye.
the
Arhit.
thing is,
Any?
sir.
Yeah.
uh,
Mm,
Actually, the thing is, sir, frankly speaking, this topic
mm.
is quite from means out from my syllabus because these are quite advanced level topic. I think so, because we only have fluid mechanics,
Yes.
and
Yes.
after sir
Mm.
means starting these, sir, I have means I also invested much means per video I
Yes.
invest
I
like
can see that. Mm.
because sir that from that book also I had to study and
Yes.
the thing is, sir, this exam, the exam
Mm.
of NPTL, has been scheduled
Mm.
in between my semester exam. So that was
Okay.
why, sir, I am finding it difficult to revise on these things.
It's not an
Uh,
issue. You can attempt this exam as many times you want, but primary thing is your academic exams, right?
yes, sir.
So you
But sir,
focus on
actually, due
those
to my
exams.
yes, sir. But due to my interest,
Mm.
sir, I find it very interesting to learn this. So I study
I
regarding it, sir.
appreciate that. I appreciate your efforts. Yes, yes. It's good. It's good that you're learning other concepts other than your academics. It's helpful for you in future.
Yes,
But
sir.
your grades are also so important for your academics and for your further studies.
Yes, sir.
Okay?
Yes, sir.
Yes. Okay, Arhit. Thank you so much. I will
Thank you,
see
sir.
you in the next session. Yeah.
Thank you, sir.